Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video, we are going to continue our efforts in just doing that, and just to remind you that we are currently in the solve linear elastic function, and we're basically stuck here in the calculate global stiffness matrix. And now for each one of those FEMBarSprings, we need to do all those tasks to get the global stiffness matrix. And for each one of those beams, we need to do the same tasks. And in this video, I'm going to try my best to tackle as much as I can from those things, but of course not all of them. And before I start, I want to give a reminder that this video is part of its own video series about the finite element method, linked in the top right. And of course, there is another playlist that only deals with programming, also linked on the top right. You can check it out. Furthermore, I want to mention that all channel members have access to the source code. However, if you are not a channel member, then don't worry, because every single line of code will be written in front of you. You can write along and you will have the exact same code as I have. So without further ado, let's jump into the video. So sit back, relax, and enjoy the show. Alright, now we need to go to FEMBarSprings because we are going to define those functions. So let's go to the FEMBarSpring here and let's start defining our functions. I'll go back very quickly to the controller and copy this entire thing because I want to kind of just define for now and think about it later. So in the FEMBarSpring, I think I've written this before. This is the region where stuff will happen. Let's give it a region name here and say FEM calculations. This is where the FEM calculations will take place. Those are the functions I need. So now I need to define them. So function, nothing will be an output void, so nothing. Calculate local stiffness matrix. Now because we are in MATLAB, I always need to pass in the reference to its own self, or in C# it's called this, by the way, but you need to pass it manually here. So we define this. Now I also need to define the function, calculate transformation matrix. Once again, I need to pass in the reference of the object. And also I need to define the function calculate global elemental stiffness matrix. And once again, pass in the object. And also function calculate global structural stiffness matrix. This is not going to be the cleanest way to do in terms of memory. It might cause a memory drain, this function. I'll talk about this later. And function initialize. Wait, there is a typo. Let's go back to the str controller. There is a typo here. So initialize. Okay, so let's go back to FEMBarSprings and initialize local equivalent nodal load matrix. So initialize local equivalent nodal load matrix. And here I need to pass in the object, and I need to pass in the number of load cases, because that is what we pass to it. Now those functions are what are called in the controller, and I need to copy paste the exact same functions and the FEMBAR beams, so that at least the code is working. Because so far the code is broken. You know, we tried this in the last video, and it tells you that those functions are not defined. Now we're defining them. So let me make a same here in the FEMBAR beam. Here I will call this FEM and push the enter key and control. Now, for those of you who are programming geniuses, I know that there is a better way of doing things. You could define a base function. Let's call it FEMBAR beam, for example, and include most of the common functionality, because you can see in the FEMBarSpring, you can see this is common, you can see those are common, even everything here is common. You can see that those are common, and even those are, wait, what? The only difference between the FEMBAR beam and the FEMBarSpring is basically here. The FEMBarSpring has those, and the FEMBAR beam hasn't. So okay, I just copy pasted this stuff. So if I run the main now, it should be working. So let's just run it and see what happens. The errors should subside because now all the functions have been defined, and the errors did not subside. Well, what a shame. Unrecognized method property, global stiffness matrix. I remember from the previous video. Yes. This is from the previous video. There was something about, wait, what's it? STR controller line 805. That's the one. Here in the previous video, I was like contemplating what's the name of that thing. And it's not the global stiffness matrix. It's actually the global stiffness structural matrix, right? That one. So I'll go here and to the controller. That's a source of error. Let's change that. Wait, what? No, that's a source of error. And that is a source of error. So let's run again. Oh, wait, I cannot run here. Let's run again. There are still, what's that? I have a lot of errors here, it seems. So array have incompatible sizes for the operation. Ah, yeah. Okay. Now this is an error I cannot avoid for now. I can't avoid it because, let me show you what the problem is. So if we run the main, I cannot avoid that because I still haven't produced the matrix. The problem here is that the global stiffness matrix has been initialized, which is 66 by 66, but this one hasn't because I haven't done anything with that. So of course it doesn't allow you to add those things. Now this is something I cannot simply fix here because I need to program it inside the FEMBarBeam and FEMBarSpring. So just to check if the code is running or not, let me comment it out. I just want to see if the code is going on full circle. Okay, at least the code is running full circle, so there are no big blunders. Now I'm gonna uncomment this and keep it tabbed because those two dudes need to be defined, and I will define them later. So let's dive into FEMBarSpring. Now, for FEMBarSpring, the stiffness matrix, the local one, is not going to be that crazy. So first of all, we need to initialize this entire thing. So object.local stiffness matrix. This is going to be 0s, 12, and 12. Now you might think, why 12 and 12? Because a line has two nodes, which means that it's going to be a 12 by 12 stiffness matrix. I don't like reusing magic numbers, but in this case, it's an exception because we know exactly that's 12.12, unless you are a FEM genius and you will use a higher order bar. But of course here, I'll keep it for now 12, 12. Now we need to start filling it in. It's going to be zeros everywhere with some exceptions. So local stiffness matrix here for the for the 1 degree of freedom, that's the axial degree of freedom, it's going to be KUX. I think I should call object.KUX. That's true. And now I need to copy paste this stuff. So let me just copy and paste it a million times. For the degree of freedom YY, it's going to be KUY. KUZ for the degree of freedom ZZ. This is the main diagonal of the stiffness matrix. Now we need to deal with the off diagonals of the stiffness matrix. Now, the transformation matrix has been explained in my previous videos in the Finite Element Method series. Well, let's create our transformation matrix. The transformation matrix depends on the direction cosines, or in other words, on the local axis vectors. And it's not really that complicated. Let's dive into it. So first things first, the transformation matrix is once again going to be a 12 times 12 matrix because those are the degrees of freedom. So here I'm going to say object transformation matrix. Is it transformation matrix? Yes. Okay. This is going to equal zeros of 12 and 12 because once again, those are the degrees of freedom. Let's dive into it. So first of all, if you remember in that video, there was something called lambda. So lambda in this case is going to be zeros of, 3 and 3. Now we need to fill in the lambda. Filling in the lambda is actually really, really easy. The lambda is going to be for the first row, is going to be the unit vector of x. For the second row, it's going to be the unit vector of the y. And for the third row, it's going to be the unit vector of the z. I can actually change the definition here and say here, object.vx, and then semicolon to open a new line, object.vy, and then semicolon to open a new line, and then object.vz. That's all there is to. Now, I can basically fill in the transformation matrix. So now, for the first column to the third, for the first column to the third. So this is the first block. This is going to be lambda. And then I need to fill the other consecutive objects or blocks. So this is going to be from 4 to 6. That's going to be from 7 to, wait, what? 7 to 9. Yep, 9. Because 7, 8, 9. That's going to be from 10 to 12. Of course, the same thing applies here. 4 to 6, 7 to 9, and 10 to 12. Fantastic. So this should be the transformation matrix. That's it. We're done with the transformation matrix. We can go ahead. Now, let's go to the next thing that I might do, which is basically the elemental stiffness matrix. For that one, that's very easy. The global elemental stiffness matrix, that's I think, let me remember, this has been explained in one of my videos, I forgot which one. And in this case, object.global elemental stiffness matrix equals object.transformation matrix transposed multiplied by object.local stiffness matrix multiplied by object.transformation matrix. Now, for the details of that, please refer to my Finite Element Method videos. Now, for the global structural stiffness matrix, that's going to be a little bit more complicated because, first of all, it's a memory drain. I'm going to define something called kg, basically. This is going to be zeros off. Now, here, I'm going to put all the degrees of freedom of the structure. Because I'm kind of lazy, when I assemble the stiffness matrix, I want to assemble it here rather than assembling it here. So you can see how the assembly looks in my controller. You can see I'm just adding. So this must have the same size as this, which means this is a memory drain. And I agree. I want to say that this is a place where memory gets drained. There are much cleaner ways of doing things, but I will just keep it for now to keep it simple. Tell me in the comment section if you have codes that are more cleaner. One alternative is to not even calculate this big global structural stiffness and just basically add it here. Here, do some assembly here in the controller instead of in the element. But here, of course, if you want to calculate the structural stiffness matrix, I need to give the size of it. So I say here, size of object.global stiffness matrix. Yeah, I'm passing in the size here. Of course, I must pass it in both this and this for the FEMBAR beams and the FEMBAR spring. And you can see how not using inheritance comes back to bite me. Because now, since I changed something, I need to change it in two things. I need to change it here, which I'll come to that later. With here, I put a size. Oh, wait, that's a function name. Matrix size. And here, actually. And in the FEMBARSpring, I must pass in the matrix size. What did I call it? Matrix size? Matrix size, yes. So here, comma, matrix size. See, if I used inheritance, I only had to change one of them and the other one would be perfect. Here, I'm going to declare for the matrix size, the kg, and now we need to start filling it in. What is my objective here? Let me explain this to you. The stiffness matrix can be split into 4 blocks. I've done this in the Finite Element Method explanation series, but I'll do it here very quickly. Every single stiffness matrix can be subdivided, at least for bars, can be subdivided into 4 blocks. Node 1 with node 1, so node 1 with itself. Node 2 with node 2, so node 2 with itself. And those are usually on the main diagonal of the stiffness matrix. Node 1 with node 2, and node 2 with node 1. And those are the off-diagonal terms. And we need to take those 4 blocks, slice it and dice it, and place those 4 blocks in their corresponding places in the global stiffness matrix. That's our objective. We can do it here, which is actually a memory drain, or we can do it here, which would be cleaner in terms of implementation. I keep this as a homework for you. If you want to try implement it here, I want to implement it here, despite the fact that I am very well aware that this is a bloody memory drain. So kg equals zeros. Now I need to cycle through the fem nodes. So here, let me just fish them out. Fem node 1 equals, object.fem node 1. And fem node 2 equals object.fem node 2. Okay. Now, from the ID of the FEM node, I can know its position in the global stiffness matrix. So now here, let me just put a comment here and say block FEM node 1 with FEM node 1. Okay. Now this block has a starting column and an ending column, and a starting row and an ending row. I need to know exactly where those are. I can know them from the ID of the FEM node 1. So let's do that. Starting, now I must debug this definitely. Starting column is going to be FEM node 1.id, because it might be ID 5 or something. FEM node 1.id minus 1 multiplied by the degrees of freedom plus 1. Let me explain this to you in action. Let's say that FEM node 1 is actually ID number 1. In this case, this would be 0, so the starting column would be column number 1 in the stiffness matrix of the global structure. If this is, let's say, FEM node number 5, then 5 minus 1 is 4 multiplied by 624, so the starting column is 25. Because every single FEM node occupies a 6 by 6 space in the global stiffness matrix. So I need to know exactly where the starting and where the ending of that occupied space is. That's a starting column, which means that's easy now. The ending column is going to be the starting column plus 6, or plus of FEMBarSpring.dof. This is FEM node 1 with FEM node 1. Similarly, I must take the columns and I must take the rows. So I'll copy and paste this, and I'll say here, starting row and ending row, which means here I must copy this and paste it here. And this is going to be the same thing. FEM node 1 ID minus 1, FEMBarSpring degree of freedom plus 1. Now I can use it to fill in the stiffness matrix. So let's fill it in. Let's push the enter key here to kind of make sense. KG is going off starting column. Wait, no, we give the row first. Starting row to ending row, and starting column to ending column. This is going to equal the local stiffness matrix of the first sector. So object.local stiffness matrix of the first sector, 1 to 6, or degrees of freedom. Okay, local stiffness matrix 1 to 6, 1 to 6, because we're dealing with node 1 and node 1. Okay, let's go now for block FEM node 2 with FEM node 2. I can copy this entire thing, paste it here, and say now this is FEM node 2 with FEM node 2. This is the second block on the diagonal. We're going to do the same thing. However, this time our focus is with FEM node 2, not FEM node 1. And since we are in FEM node 2, the stiffness matrix is 7 to 12 and 7 to 12, because we are in the second block, or the second block on the diagonal. Now things get tricky here. I'll copy this entire thing and paste it. Wait, what? I made a mistake in pasting. Now this is FEM node 1 with FEM node 2. So this is the block on the top right of the stiffness matrix. So its columns are controlled by FEM node 2, and its rows are controlled by FEM node 1. Right, so this is true, and that needs to be changed. Now, since we are taking the columns from FEM node 2 and the rows from FEM node 1, this should become 1 to 6, because FEM node 1. Now I can copy this entire thing, paste it here, and now say FEM node 2 with FEM node 1. So now I should flip. This, wait, did I mess up? I don't think so. This becomes FEM node 1, this becomes FEM node 2, and this becomes 7 to 12, and that becomes 1 to 6. Okay, now I think this is how the global stiffness matrix gets assembled. Object.global structural stiffness matrix is going to be KG, the thing that we were defining. Okay, fantastic. So this ends this. Now we need to initialize the equivalent stuff, which is this one. That's the last one. And I don't think I need that, because those are springs, and springs will never have distributed loads on them. So there is no equivalent local stuff, blah, blah, blah. I don't think this will happen. We almost finished the spring. Now I need to copy some stuff to FEMBarBeam, because there is some stuff that just can be copied directly without any issue. You see, the only thing that changes between those two elements is the command calculate local stiffness matrix. The rest of the commands are matching one-to-one. Yet again, another thing that should encourage any one of you who is well adapted or well versed in programming to implement an inheritance scheme here. I'm not doing that. So I think we just finished a massive chunk of coding in this session. I don't know how long this is, but we really did something good today. We really reached a big milestone today. So yeah, I think that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a massive progress-sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.